Hi there, I'm Sean Wilsey. I'm the geology professor at the College of Southern Idaho, and I just put together a little video here to try to explain a little bit of information about the earthquake that occurred yesterday on March 31st here in Idaho. Today's April 1st, Wednesday, and I just wanted to share a little bit more information than I did. I put together a small video yesterday with some information, but I wanted to share a little bit more information, had a little more time to digest the information and look at some of the geologic data. So I wanted to share that with some folks that might be interested. First thing, just some of the basics about the earthquake. It was a magnitude 6.5 quake. It was located about 20 or so miles northwest of Stanley, so sort of in central Idaho. Good news is there was no damage, no significant damage, no injuries or fatalities, so that's great news. But it was felt by a lot of people, not just in Idaho, but throughout the Pacific Northwest and the Intermountain West. There was some interesting reports about how people felt the earthquake and their perception of it. Some people reported a sort of a nauseous feeling or kind of a rolling feeling, like they were on like an amusement park ride, something like that. Those are caused by, that type of motion is caused by what we call surface waves. So in an earthquake, there's actually three different sets of waves that come in, three different sets of seismic waves that come in. Let me see if I can show this to you here. And so if you just, this is just kind of a generic earthquake here. So there's an initial wave that comes in. This is called the P waves, or the primary waves. Usually people don't feel these. These are compressional waves, so they're sort of like an accordion or a spring. They kind of move by compressing and extending over time. Then there's a second set of waves that's usually a little bit bigger. This doesn't show that, but these waves should be a little bit larger. These are the secondary waves, or the surface waves, which have up and down motion. And then the most dangerous waves, of course, are the surface waves. So these are the ones people typically feel. These are the ones that cause the most damage. But these are the third set of waves that show up at during an earthquake. So depending on where you were, you might have felt the earthquake a little bit differently. Depending on the type of house you're in, that can affect how the earthquake is actually perceived. Depending on what kind of rocks or subsurface materials are underneath your home or the building you're in, that can affect how the earthquake is actually felt. It was actually interesting when the earthquake happened yesterday. I actually didn't feel it. I was moving a couch in our basement, so I was kind of like moving. And so if you didn't feel the earthquake, it might have been because you were moving. It seems like most of the people that felt it were stationary, awake, alert, and they were the ones that felt the shaking, which lasted in most places in southern Idaho anyway, about maybe 3 to 6 seconds, somewhere in that range. But yeah, so there's different ways that the earthquake was actually felt. And immediately my thought went, once I realized, okay, we have had an earthquake and I could see our light fixture swaying a little bit, my immediate thought was, well, it might be a bigger quake happening down in northern Utah. They had just had a 5.7 earthquake about a week or so ago. So I immediately thought it was something like that. And we'll come back to the location here. The location of this earthquake is a little bit different. So this map here actually shows you the earthquake epicenter here with the little star. And then all these blue boxes here, this is actually the area the earthquake was felt in. So these are regular citizens like you and I that have gone onto the USGS website and reported how the earthquake felt to them. There's a simple survey you fill in, and you can put all that in there, and then the computer puts together all this data to compile what's called a shake map. So this is a map compiling how the earthquake was felt. So a lot of times when we talk about earthquakes, people think about magnitude, right? This earthquake had a magnitude of 6.5. And magnitude is just an expression of how much energy it released. How much energy did the earth generate when the earthquake took place? But what we're really seeing here is this really doesn't necessarily reflect magnitude, because this is something we call intensity. So the intensity of this earthquake is how the shaking is perceived, and intensity can vary depending on where you're located, again, what type of building you're in, subsurface materials, that sort of thing. And so this is an aggregate of all the data that's been put in. I think there's probably, I could go back and check here, but you're looking at thousands of responses from regular folks that have gone into the USGS database and reported how the earthquake felt to them. So if we just click on one of these boxes here, just arbitrarily, this represents 8 responses from 8 different individuals at this distance from the epicenter. And this MMI, this is called the Modified Mercalli Intensity Scale. So this is a different scale than the magnitude scale. It uses Roman numerals, and it goes from Roman numeral 1 all the way up to Roman numeral number 12. So 4 is kind of like light shaking, you know, you're aware of it. Maybe some fixtures in the house are shaking, that sort of thing. As the colors increase in intensity to yellow, to greens, and yellows, and then into oranges, the intensity is getting a little more severe. So you can see this is based on one response, so it's a little bit skewed data, but you can see this is up to intensity level 7. So basically, based on what this person said they felt in the earthquake, and of course, you know, realizing that you know, human responses would be somewhat subjective, the shaking level was up to about a 7 there. And what this does is, by getting more data from more people, you can kind of you get kind of a better average. You know, you kind of, it might take out some of the people who might be embellishing or maybe sort of over emphasizing some things. And so some of these are low, but then there's a lot of them. There's 33 responses over here in the Boise area, 201. So these are the larger urban areas over here. This is Nampa, 771 responses. So kind of interesting, but interesting to see that was felt from British Columbia down into Nevada and Utah, over into Montana and Wyoming, and into Washington and Oregon. One reason I think that we might be seeing, another thing to notice here is that there's not a lot of little squares of responses close to the epicenter. And if you know anything about Idaho's topography and just sort of layout, is that this is an incredibly rugged mountainous area here in the central part of the state. And so there's consequently not a lot of people living there to have reported it. So there's not a lot of residences and towns in that area. One reason I think that maybe the earthquake was transmitted so far, or felt so over such a large distance, might be the rocks that it was traveling through. This part of the state has a lot of granite, a very hard, resistant igneous rock. And these types of rocks transmit seismic energy much more effectively. It's kind of like taking a bell and tapping it with a hammer. The whole bell reverberates and rings. And so we're seeing some of the seismic energy radiating out over a pretty large distance here because of that. So anyway, that's the shake map here. A couple other things I wanted to share with you. This is the Google Earth. So sort of zoom out here a little bit. I think most people know where the earthquake occurred. Here's Highway 75. Here's Stanley. This is Highway 21. Banner Creek Summits right here. And this is area here where the road takes a big bend here. This is the Cape Horn area. And so this is kind of an odd place for an earthquake in Idaho. If you think about all the places we've had earthquakes historically in Idaho, this seems at first glance to be a little bit out of place. And so I want to spend some time maybe thinking about and discussing with you why we had an earthquake in this location. And so to do that, I'm going to start with kind of the big picture. Let me grab a different graphic here. We already talked about that one. So if we zoom way out and just talk about what's going on in our part of North America, what we can see here over here on the left is you and I here in Idaho are part of the North American plate. And off to the west, across the San Andreas Fault, there's another plate called the Pacific Plate. And the Pacific Plate is moving rapidly, geologically rapidly, past us, moving up to the northwest. And as the movement takes place, that generates earthquakes along the San Andreas Fault, which everyone has heard of, and all the earthquakes in California are part of that process. But it's not as simple as this graphic would show. While this is the actual plate boundary here, some of the stress from this motion is transferred into the plate. And really these arrows are sort of like, again, the big picture, sort of the generic broad view of what's actually going on. In reality, what's happening, if you kind of move into this diagram here, here's the Sierra Nevadas in California. This is Nevada. There's the Great Salt Lake. This is the Wasatch Range of Utah. Here's the Snake River Plain of Idaho. And here's the central Idaho Mountains. Really what's happening from the Cascades and the Sierras over to the Wasatch and up into southwest Montana is this entire portion of the Intermountain West is being stretched in sort of an east-west fashion. And what that does is over time, as we get earthquakes, the earthquakes typically occur by faults moving up and down. So we get mountains being pushed up, valleys being dropped down, and this is sort of the topography we see across Nevada, western Utah, and even up into parts of Idaho. If we look here at, let me switch back again over here. If we kind of look at where the last big earthquake occurred in Idaho, so here's the craters of the moon area. This is sort of the eastern part of the state. Chalice is up here. But what you can see here is we have these a big valley. This is the Lost River Valley, the Lost River Range, another valley, the Lemhi Range, another valley here, and then the Beaverhead Mountains, which kind of run along the Idaho-Montana border. These mountains and valleys were created by this faulting activity. So the extension, sort of southwest-northeast extension, stretching, if you will, of the Earth's crust has caused these mountains to be pushed up while dropping the valleys down. And of course, the last big earthquake was over here north of Mackay near Boar Peak. And so that's the Boar Peak earthquake. And that tallest point in Idaho is there because of earthquakes. So earthquakes happening over, millions of years, thousands and thousands of earthquakes have pushed up these mountains to create some of the highest points in Idaho. So hopefully that helps a little bit with the tectonic setting a little bit. To go a little bit closer in view, let's switch over to this guy again. And let's look at just historically where we've had earthquakes in the past. And so here's Utah, Idaho, Wyoming, Montana. And there's a bunch of numbers on here. The size of the circle corresponds to the magnitude of the quake. So these are historic earthquakes. These are quakes that have happened since, the pioneers have come across and settled the West, that people have felt. So you're looking at, maybe 130, 140 maybe years of earthquakes being felt, maybe not recorded with seismograph stations, but felt, recorded historically somehow. And you can see those here. So the biggest of the biggest two here are the two blue ones. And sorry, so this one here is the 1959 Hebgen Lake earthquake, and this is the 1983 Boar Peak earthquake here. What's interesting to note here is, lots of earthquakes down in the Wasatch, coming up towards Yellowstone, and then heading up into Montana. But look right here at number 10 and 11. These are basically really close to the epicenter of the earthquake that occurred just yesterday. And so these two happened in 1944 and 1945, so within about a year of each other, and they were about magnitude 6. So similar magnitudes and similar locations to these quakes. Not much on these earthquakes. Again, back in the 40s, there was even fewer people in the area. These quakes were felt in Boise and all the places that you'd expect them to, just like the earthquake that happened yesterday. But I guess the point here is we do have a historic record of earthquakes in this region. So it really shouldn't come as a huge surprise. And this was something I had to kind of dig in and find out. I didn't know about these two earthquakes historically. So that was kind of interesting to me to see that. So in a broader sense, the earthquake yesterday, which I've located here with a star, is actually part of a zone of known historic and prehistoric earthquakes. This is called the Central Idaho Seismic Zone. This is part of this, again, this seismic belt that runs from southern Utah up through eastern Idaho, right through Yellowstone, and then up into Montana. And so you can see these clusters of earthquakes. In fact, it's been in the last decade or so, there's been smaller clusters of earthquakes near Chalice. There's the Boar Peak earthquake over here, the Sawtooth down here. And so this earthquake here that happened yesterday is sort of at the western edge of this area of known seismicity. So again, this earthquake isn't too surprising in its location based on what's happened in the past. I guess the key thing to point out here, because sometimes people get a little bit panicked about these things, is this, again, this earthquake is not on the same fault line or the same system that produced the Boar Peak earthquake. I'll show you some other evidence here in a minute that shows that it was a completely different type of fault motion as well. Furthermore, this earthquake had nothing to do with any activity in Yellowstone. So rest your fears. There's no reason to believe that the earthquake yesterday, which was hundreds of miles away from Yellowstone, is going to do anything to change what's happening underneath Yellowstone. So we can throw that out the window pretty quickly. Okay, so the last thing I want to look at here, if you guys find this interesting and you're still with me here, is how do we know what kind of fault produced the earthquake? And to do that, what we can do is, remember the first diagram I showed you with the P waves, those first little compressional waves that kind of push-pull, spring accordion type waves that come in initially when an earthquake occurs. It turns out that the very first movement of the earthquake can either be compression, which if you look here actually pushes the little line up, or it can be, I'll just change this word dilation to extension or pulling, or it can be down. So by looking at, if we have like an array of seismometers recording the earthquake, and as those first P waves come into each station, by looking and seeing if the rocks are being squished or if they're being stretched, we can take all that data from all those locations and we can plot that data up to figure out what kind of fault and what kind of fault motion produced the earthquake. And so there's three fundamental types of faults. And what you get then is when you plot up these zones of rocks being squished or rocks being stretched over a geographic area, you get these funny little beach ball shapes here. And I want you to think of these as having a compass direction. So north would be up, east over here, south, and west. And so we get specific patterns depending on the type of faulting involved. The black areas on all of these show places where the rocks are being squished, and the white areas on these three little beach balls are where rocks are being stretched. And so by looking at the pattern we get over the region, we can see where the rocks were stretched and where they were squished. It also shows us the lines on these, so whether it's this one here with this kind of like X kind of line, or these sort of lines on this one or this one, the lines also show us the orientation of the fault. So the actual place where the rocks broke and slid, the actual planar surface in the earth that's caused the earthquake to occur, we can actually see how that is oriented. So let me show you the one from yesterday and see if this makes any sense, if you're still with me. So if we go into yesterday's earthquake, there's all sorts of good information here on the USGS website. Some of it you might be able to figure out. Some of it's kind of technical, but take a stab at it. So sure enough, it shows this fun little beach ball shape here. And notice that this is similar to that one that we saw that looked like strike slip. So notice the seismic data is showing us that this earthquake happened either on a north-south trending fault or on an east-west fault. Well, the one thing I did to kind of figure this out is I went and looked at a published geologic map for the area. So this is Highway 21 here. So there's Cape Horn right there at the curve of Highway 21. Stanley's down here to the right. Banner Creek Summit's down here to the left. And sure enough, the highway, and in fact the creek, is following a fault here. So this black kind of dotted line is a fault system. It's a fault system that's partially covered, which means it probably hasn't been active for a while, but it actually shows, not perfectly north-south orientation, but something kind of close. So the most likely solution for this earthquake is that it was on a north-south fault. And with this being the zone of compression and this being the zone of compression, what that means is that the east side of the fault moved to the north relative to the west side, which moved to the south. Or in other words, this is what we would call a left lateral strike slip fault. Again, if you don't get that, that's okay. But basically, the fault has moved sideways. So the earth has actually broke, the rocks have been under stress, and the east side of the fault moved to the north, and the west side of the fault moved to the south. How much did it move? No way of knowing for sure right now, but based on the size of the earthquake, we're probably looking at maybe a few feet at most. There probably isn't anything to see at the surface, so there's probably not some gash under the snow through the ground. It would probably take something a little bit bigger than that to produce some type of movement like that. So anyway, so let's see if I have anything else. I think I've kind of gone through all the cool stuff I wanted to show you there. Yeah, more or less. So just to conclude, we live in the 6th most seismically active state in the country. Earthquakes are what has shaped our landscape. Earthquakes are what have caused Idaho to have great, beautiful, lofty mountains that we go skiing and recreating in the winter and in the summer. Earthquakes are what have pushed the Sawtooth Mountains up to produce one of our most iconic mountain ranges. The Tetons over in Wyoming, same thing. So a lot of the big, magnificent, inspiring mountain ranges you've seen are the result of earthquake activity. And so this is nothing new. This is something that happens. So we shouldn't expect anything, sort of out of the ordinary with this. Last thing, I guess, here, this is actually the last 2 days. This is earthquakes that have happened in the last 2 days. So I'll kind of zoom in here. You can see a bunch in California, a couple up in Utah. So Utah's still dealing with some small aftershocks from the earthquake they had in Salt Lake City a few days ago. And here are the ones in Idaho. So the big orange circle there, that's the main quake, the 6.5, and then you can see all these aftershocks happening around it. Interesting that the aftershocks are mostly to the southwest of the epicenter. That sort of suggests to me that maybe the motion was mainly with the west side moving to the south versus the east side moving to the north. So if really this side of the fault stayed put, but this side had the motion, that would make sense that you'd have all these aftershocks. And aftershocks are nothing more than, the earthquake, the earth has moved, the fault has slipped, and now it's just readjusting to its new stress conditions, and so you're getting some little adjustments to that there. So that's as of today, but we would expect these to continue. Some of these, 4.4, there's a 4.1, there's a 4.6. Most of these shouldn't be felt, for the most part, to people in the Snake River Plain down here in Twin Falls. Maybe folks in Boise who are a little bit closer might feel some of these, but again, the shaking's going to be really, really light. And maybe one final thing I can do, and then I'll sign off on this, is, let's see, let's do this real quick. Explain to you how earthquake magnitudes sort of compare to one another. So for example, there's just a blank screen, right? So yesterday we had a, let's see, how big was our earthquake? It was 6.5, okay? This is the Idaho earthquake, okay? Utah had, sorry about the terrible handwriting there, their earthquake was a 5.7, okay? So they had a 5.7 earthquake about a week or so ago. So one question you might have is like, well, how do you compare these two? Like, how much bigger? We all know that the 6.5 is bigger than the 5.7, but how big is it really? So there's actually a pretty simple way you do this. To figure out the difference between these two earthquakes in terms of their energy, you just take the 6.5 and subtract the 5.7. This is exciting doing math for everyone. And you get 0.8, right? 0.8. Well, now what you do is you take the number 32, and this number here becomes the exponent to the 32. So it's 32 raised to the 0.8 power. And so that's because earthquake magnitudes, the magnitude scale we use, it's logarithmic. It's an exponential scale. Again, I'm probably losing you with the math. So if you crank this out on your calculator, you get the number 16. What that means then is that the earthquake we had in Idaho yesterday on March 31st released 16 times more energy than the 5.7 earthquake down in Salt Lake City. In other words, if you take 16 5.7 earthquakes, that equals the energy of one 6.5. So one of these Idaho earthquakes we had yesterday would be equivalent to 16 of these Utah earthquakes, to kind of put that in perspective. So hopefully that helps a little bit. I think everyone intuitively knew or knows how that kind of works, but that may or may not help a little bit. So anyway, hopefully that helps. Hopefully you've enjoyed some of this geology analysis. Hopefully everyone enjoyed the free ride that the Earth gave you yesterday with a little earthquake. You can check that off your bucket list. And really, again, just to calm everyone's nerves a little bit, really in the grand scheme of things, in the midst of a really scary pandemic, if we're going to have an earthquake, this is the perfect earthquake to have. A good sized earthquake that releases a lot of the Earth's stress in an isolated, uninhabited part of Idaho where we have no damage and no casualties whatsoever. So we'll chalk it up as a win. And everyone stay safe out there, and feel free to send me questions. You can direct those to me through my email. It's swillsey@csi.edu. Or you can comment, if you see this on Facebook, you can comment there and I'll try to answer any questions you have. Have a great day. Thanks.